All right, we're going to start section 7.3, and this is titled Rules of Replacement 1. And the first 8 rules of inference in 7.1 and 7.2 are called rules of implication. Okay, when we get to 9 to 18, the next 10, these are going to be called rules of replacement. And the difference is a rule of replacement. Think of you have a compound expression. It can be replaced with another expression that's logically equivalent, which means if I did truth tables for each of those expressions on either side of a symbol, and the symbol is going to be right over here, this double colon. Okay, we're going to use the double colon, and it means that the expression on this side is the same as the expression on this side. Okay, and I'll tell you what those expressions are. They call the whole thing, replacement expressions. If I did a truth table for this expression and did one for this one, when you look at the final columns, you'll notice that on every line it's the same. If the first line is false on one, it's false on the other expression. True, true in the other. Every line is the same. And if you go back to chapter 6, when you were comparing propositions, 2 propositions were logically equivalent if they had the same truth value on every line of the truth table. So if they're logically equivalent, then you can replace them. If you have one expression, but you can replace it with a different way of putting that expression, and that helps you derive the conclusion through natural deduction, well, rules of replacement can come in awful handy. And I'll give you some examples, and we'll go through this. This will keep making more and more sense, okay? So one thing, let me read here the handout, and we'll get to some examples, okay? So we will now begin to look at the first 5 rules of replacement stated in the form of logical equivalences. A new symbol will be used, the double colon. As I said, this just means whatever expression's here. The double colon means the expression on the other side is logically equivalent. Hence, they can be interchanged and replaced. So you could go this way. If you had something here, you can replace it here. If you had something here, you can replace it with the other expression. Okay? And this symbol asserts, this is repetitive here, but repetition is good, that the expressions on either side of it have the same truth value. Also, underlying the use of the rules of replacement is an axiom of replacement. And all this means, everybody, is logically equivalent expressions may replace one another, either a whole line, this will make sense when we start going through examples, or even a part of a line. So let me show you what I mean by here. Okay, let's say your first premise is, if S, then it's not both T and U, okay? Now this here, you don't know this yet, but you see this consequent, not both T and U? That is logically equivalent to this expression. So if I was going to go over here, it's not both T and U. That is logically equivalent to either not T or not U. Now this is called De Morgan's, which I'm going to show you in a minute. But if these two are logically equivalent, this is right here, right? I can replace that with this one right here. And that's why you get if S, then it's not T or either not U, and you use De Morgan's. You replace this expression right here, can be replaced with that one. Okay? But this is only part of the line, right? I didn't do the whole line, I just did this part here. So the axiom of replacement, logically equivalent expressions can be interchanged with part of a line, which we just did the consequent here, or it could be the whole line. Let's say the whole line is, it's not both G and K. Well, that can be replaced with either not G or not K, De Morgan. So there's a couple examples of the axiom of replacement, a whole line right here, or just part of a line right there. And since I've been using De Morgan's, let's just get into the rules of replacement. I'll explain them to you here, so you're familiar. I use De Morgan's. Well, here it is. Rule of inference number 9 is the first rule of replacement. And this is called De Morgan's rule. And notice with this. If you have not both P and Q, that can be replaced with either not P or not Q. What's significant is you can turn a dot into a wedge. So a dot operator can be changed to a wedge operator, or a wedge operator can go to a dot. Okay, remember, pay attention to these operators. They can really help you see what rule of implication you can use or what rule of replacement. So a dot can go to a wedge, but let's say you have disjunction here. Neither P, not either P or Q can be replaced with both not P and not Q. So here you could even go this direction as well. Alright, so why don't I do a truth table here so you guys can see, logically equivalent. Let me just bear this out. So if we had, it's not both P and Q, and we were going to compare that with either not P or not Q. If I do the truth table for these two expressions, we should have the same truth value on either line. So let's do the truth value. It'd be true, true, false, false, because there's only two simple components. And remember, when you're comparing what P is here, you make P the same over here. And then Q is going to be true, false, true, false. So over here, true, false, true, false. Let's change the ink to red for this. Okay, so let's do in here, this will be true. We're dealing with a disjunction. So you remember, you'd have your operator tables out. This is false, that's false, and that is false. Over here, this is false, false, true, true. This one here would be false, true, false, true. Let's go right here. So if we were going to do in the middle here, false, false for a disjunction is false. False, true is true. True, false is true, because with the disjunction, all you have to see is at least one true. So there is the final column for that. This one here, if this is true, this is false. If this is false, that's true, true, true. So there is the final column here. First line is false, false. True, true. Third line, true, true. Fourth line. So they're logically equivalent, right? That's why, now you know through a truth table, this is why if you have this, you can replace it with this. If you have this, you can replace it with this, and they go either direction. Okay, so you want to, use the flap in the back of your book for this, and just to, you're going to have to refer to that, because sorry, I'm losing my train of thought here. You'll have to refer to the flap in the back of your book, because some of these are going to take you a little bit to memorize these. That's my point, okay? But you want to get conversant where you can go either direction. So that's De Morgan's. Let's talk about commutativity. Now here's the thing. You remember when we keep loading you up with stuff, you go, oh no, this is more, I'm panicking. You don't have to panic. De Morgan's you kind of have to think about, but commutativity is an easy one, okay? So this is not that bad. All this is saying is, if you have a disjunction or a conjunction, you can switch it. So either P or Q can be Q or P. If you have both P and Q, you just switch P and Q, and it could be Q and P. So, if you have either P or Q, you want to switch them. The order, this could be Q or P. Now, why would you ever care about something so simple? Here's why. There are people called logic Nazis. They like things done in the proper perspective. So let's say you had Q or P, and you had not P. Now we can see that not P and P cancel out, so this would be Q. But there are people in logic who get bent out of shape. They want you to, if what cancels needs to be on the left. So they'd rather you do P or Q, not P, Q, because this is what the conventional skeleton is. So a lot of people are happy with this. This gets them all bent out of shape. I think they got too much time on their hands. Sometimes if I give you some problems, I'll say, don't worry about commutativity. Other times it's a little more instructive to have you go do it. But that's all commutativity is. If you have P or Q, or both P and Q, you can replace it with Q or P, or both Q and P. That's all that is, okay? Let's go to the next three. All right, associativity, this is going to make sense from algebra. If you have either P or Q or R, that can be replaced with either P or Q or R. And here's the thing, with associativity, the operator has to be the same. It could be a wedge or a dot. So you only can use associativity if you have a wedge. It's a wedge here, a wedge here. Right there and right there. Or a dot or a dot. Here you have wedge, wedge, dot, dot. So the point is, all you're doing is moving the parentheses. You see, P, either Q or R, we just move the parentheses. This can be replaced with this because moving the parentheses, when you're dealing with an operator appearing twice here in this case and it doesn't change, they are logically equivalent. If I went and did a truth table, it would be an 8-liner. You'd have the same truth values on every single line, okay? So that's an easy one too, so you don't have to panic, even though I'm giving you more associativity. A lot of you are probably familiar with this from high school algebra. Just switching parentheses doesn't change the meaning of these expressions, okay? So the truth value of a conjunctive or disjunctive statement is unaffected by how they are grouped or associated by the use of parentheses, okay? Distribution, okay, this is from algebra, but you may have to kind of think about this a little bit. You use distribution when you have a dot and a wedge being used in the same expression. Here it's a wedge and a dot. Here's a dot. There's a wedge, wedge, dot. So distribution sometimes can come in handy. So if you have a conjunction, in here, a conjunction can change to a wedge can change to a conjunction, and depending on where you start, you go both directions, and both directions up here. They all rules of replacement. You want to get used to going this way and writing it out that way, okay? So here, if you have a conjunction, and one of the conjuncts is a disjunction, you can turn this whole expression, which is a main operator, a dot, right? You can change the main operator to a wedge and make the disjuncts a conjunction, okay? So you'll have to refer to this. Some of you that were good at algebra, this will be easy, but that is another rule of replacement, and when I give you some examples, this will make a lot more sense. And then the last one that we will look at for this video is double negation. If P can be interchanged with not P, a pair of tildes immediately adjacent to one another may be either deleted or introduced without affecting the truth value of the statement. So let's say you had something like this. Let's say you had not P, okay? And I said in ordinary English, hey, what is the opposite of not P? If you weren't even looking at this, if I just spoke to you, what's the opposite of not P? You all would go P. If you have not P and I said, what's its opposite? You'd go P. That's all we're doing here. What is the opposite? What is the opposite of not P? And that is equivalent to just P. And here they've written it P is equivalent to not P. So if you have P, that's the same as not P. Or you can take away not the two things, and it just means P. Okay, so P is equivalent to not P. And sometimes it's good to put in the double tildes because it maybe helps you keep track of the tildes, okay? But often, if you know, the logic Nazis want you to use not P where appropriate, but often you can skip that step because it's pretty obvious to you. Okay, now the best thing, let's start using some examples of how these rules of replacement with the rules of implication that you've learned, 8 rules of implication, there are 10 rules of replacement. Let's do some examples. I have a couple here written out, and we'll do those first. All right. So here, you know the drill. We want to get not B, right? So I see a B there, and I do notice from the rules of replacement, if we have not both B and C, I can use De Morgan's, and that equals either not B or not C, right? I can replace it with that. And if I want to get not B, if I can get this disjunction here, you see this C? If I bring C down, I can use disjunctive syllogism to get the not B. So we're going to use De Morgan's on this. Let's do that first. So just follow through. Here's De Morgan's. And then here's the axiom of replacement, not B or not C. Okay, and that would be 1 De Morgan's. And you remember the axiom of replacement, you can replace the whole line or part. We just replace where my pen is circling, right there. Okay? Because I already know I want to get this by itself. Okay? So we need to isolate this now. And I can do that with modus ponens if I bring down the A. So you see on 2 here, I'm going to bring down A, and that'll be 2 simplification. And the reason I brought down the A is I'm going to use it with 1 to get, use it with 3 to get not B or not C, and this will be 3, 4, modus ponens, and let's do this again. There's the P, this whole thing is the Q, there was the P, and I put the Q down. Okay? And let's go erase those. Okay. Alright, so we're progressing along. Now I can get the not B as soon as I can bring the C down, but we're going to have to, remember the logic Nazis. Let's just work with commutativity. We need to first turn this around, because if we're going to cancel out the C to get to the not B, the logic people would like us to switch this around. So not B, okay, that would be 5, commutativity, 7, let's switch 2 around. C, both C and A would be 2 commutativity. And then let's do 8 over here, everybody. We'll just go over here so we don't. Okay. And 8 up here. Let's bring the C down from 7. So C, that'll be 7. Simplification, and then 9, we're home free. We brought the C down because we can use it with 6, and because not C is on the left, has a disjunct where the logic Nazis like it to be, we can put not B, and that would be 6 and 8 disjunctive syllogism. Okay? So that's how that would work out here. Okay, now, do you see when we had to switch this around? A lot of times I'm going to say you don't have to worry about commutativity, because if you have not B or not C, and you have a C, I'm going to let you just go do that. But remember, logic people want the C over here. That's the whole point of commutativity. Okay? So that's how we, and like I said, you may do this in different orders. You may do commutativity on this first. So sometimes your justification lines will be different, but the bottom line is you will have to go and you're going to have to use De Morgan's. You're going to be having simplification, all these other things. But the rule of replacement we used is I knew through De Morgan's I could get this into a disjunction. And then when I saw the C, and then this De Morgan's right here isolated, I knew I could get not B. Okay? All right, let's go to another example. All right, we've got two premises. We need to get not D and E. So here's the thing. Remember, do scratch paper if this helps you. To get D and E, I already know if we use distribution, okay, on this first premise, we can get both D and E, or, and remember, this is a dot, change it to a wedge, and you get D and F, right? Well, there's the D and E. I already knew from distribution that we could get that. So you remember, there's always breadcrumbs. And the breadcrumbs are telling me both D and E. Well, I know distribution's going to get it, and there it is, right? Okay, so let's do distribution first. Both D and E, or D and F. That would be one distribution. For, I can tell here, since this is a wedge, I see a not D or not F. If I use De Morgan's on this, I can get a not D and F, and then I can use disjunctive syllogism. So let's do De Morgan's on 2. Okay? Not D and F, that would be one De Morgan's, and if you were going to the handout, the back of the flap of your book, I use the rule of replacement and I went that direction, right? So not D and F, two De Morgan's. Then I can use disjunctive syllogism to get this. However, the logic people want us to switch things around. So let's do commutativity on line 3. Okay, we just switched the disjuncts around. That would be 3 commutativity, and then 6, we can get D and E. And if someone said, well, how did you do that? You go, well, I used line 4 and line 5 disjunctive syllogism. Okay, so that's how example number 2 would work. Okay, we'll have another video. I'll do 3 more examples on rules of replacement 1 and that'll be part 2 of this video.